So I think that's good. All right. I will, well, we have to start off finishing this exercise today. So I guess I'll just mark this as the starting point for today. Okay, so last lecture we picked up talking about visualizations for quantitative data, if memory serves. So we had finished talking about bar charts and pie charts. So we have gone through our definition base. We've just discussed the two different types of data. Well, we've discussed the difference between quantitative data and qualitative data. And we talked about how for qualitative data, you can visualize using a bar chart or a pie chart. I gave a few one example really of what each of those would look like. We talked a little bit about how you would construct them. And then we flipped over to the quantitative data side. We talked about 3 different grouping methods for quantitative data. So we had single value grouping, limit grouping, and cut point grouping. And then following that, we talked about histogram construction, where a histogram is effectively our quantitative data bar chart. The construction of the two is pretty much exactly the same. The only real difference is that with a histogram, you would connect the bars. And this is meant to represent the flow of data from each of those groupings into the next. So to represent the flow, let's say, across the cut points of our continuous quantitative data. Following that, we talked about shape. So we discussed, there's really, let's say, let's say there's 3 main shapes. There's the symmetric unimodal shape. And for reference, that would look something like this here, given on slide 25. So the first image here, this would be our symmetric unimodal shape. So we have one peak, hence uni, and we have symmetry around the middle. The other two shapes, the other two most common shapes, at least in this class, would be the unimodal right skewed shape. So that would be the second image shown here. And in this instance, when we talk about skewness, in particular right skewness, we mean the direction in which the tail of the curve is heading. So here I have labeled the skew tail, and you can see that this is moving to the positive side or to the right. So that's why we call it right skewed. So the direction in which that tail heads. And then in the bottom corner here, we have left skewness, which would be, like the mirror image of the right skewed shape. And in this case, we just have the opposite. So the left skew tail, or the skew tail heading off to the left side. All right, once we finished our discussion on shape, and as a reminder, we also did an illustration where we basically we're using these different shapes or these classifications, so the modality and the skewness or symmetry, to describe the shape of a histogram. And there's 2 examples of that on slide 26 here. And then we also went back and did one more example. After we finished that, we started talking about measures of center. So there are 3 measures of center that we discussed on Thursday. Those are the mean, the median, and the mode. Now, in each case, well, across the 3, the median is actually the only true measure of center, right? The mean will be at the center if the shape is symmetrical. So typically, we would recommend using the mean as a measure of center when we have a symmetric object or a symmetric variable. So those shapes that we had just finished reviewing, those are actually informative. Oh, sorry, what is this? Hopefully it won't restart on me. Okay, so those shapes that we had just finished reviewing, those are actually very useful because they inform the type of measure of center that would be ideal for the problem at hand. So if we have a symmetric shape, the mean will be at the center, and the mean would be the most appropriate choice for measure of center because it's actually utilizing all of the information that we have for that variable. So what I mean is the mean. Another way of saying that is when you look at the construction of the mean is found by adding all of the data, all of the values together and dividing by the number of values in the data set. So this is a statistic that utilizes every data point that's given to you. If the data is symmetric, this would be the ideal measure of center. However, if the data is not symmetric, so if it's skewed in either direction, the mean is not actually at the center. And I'm going to show you in a little bit what happens to the mean depending on the direction of skewness. But long story short, the mean just gets pulled with the skew tail. So if you have a right skewed object, the mean is going to get pulled to the positive side. And if you have a left skewed object, the mean is going to get pulled to the negative side. Right? The median in all situations is actually at the center. So the median is in some sense the truest measure of center because regardless of the shape, it will always be at the middle. But the median doesn't actually utilize the data points in determining where it is. It's simply just the value that lies at the middle of the ordered objects. So in that sense, it's a little bit less, I guess maybe you could say, well, trying to find the right word to describe that. It's not actually a function of the data. So we typically would recommend the median if you have a skewed object. The mode isn't really a measure of center at all. If the data is symmetric, then most of the values are going to be close to the median or close to the middle. And then you'll probably have repetition near the center. So the mode could lie at the middle, but it's also possible that you have a few objects that are, really far into the tail, for example, or some repetition that isn't close to the center, and then that would become the mode. So it's not really a measure of center in that sense. Okay, so typically, and I'll come back to discuss this in a little bit, for qualitative data, we only use the mode because the mode is actually only applicable, or the mode is the only statistic of the three that is applicable when the data is qualitative. For quantitative data, we can use all three, but the mean is the most appropriate if the data is symmetric, and the median is most appropriate if the data is skewed. In the exercise on slide 34, we have a data set that has two variables. The month of the year, so this would be a qualitative data, and the number of airline passengers that traveled in each month. And this would be a quantitative discrete data. This would be a quantitative discrete variable in its appearance in the exercise. So our objective is to find the measures of center for both variables. So we want to find a measure of center for the month of the year, and we want to find the measures of center for the number of airline passengers that traveled each month. The first thing that we did was order the data. The reason that we did this first is because the mode is easiest to find via the order data, and the median, we have to order the data anyways. So we just I just went a step ahead and started off by doing this. Okay, so from the order data, you can see that we have 12 observations, but when ordered, you can see the median falls in between 461 and 461. So that means that the median of the number of airline passengers is going to be the average of those two values. So as a reminder, if we have an even number of observations, the median is the average of the two middle values. If we have an odd number of observations, the median will actually just be the point that falls in the middle. Okay, so in this case, we can say that the median for this data set is 461. And then we can say something to the effect of, so the median is the halfway point in the data. So we can write something like, so this is interpretation. 50% of, or we can say, for example, for half the year. So for half the year, there were less than 461 airline passengers each month, or airline passengers. And for half the year, there were more than 461 airline passengers. Okay. So since the median represents the halfway point in the variable, so it's basically telling us that 50% of the data are below this mark and 50% of the data are above this mark. And when we talk about interpreting percentiles, I'll come back to that in a bit. This is probably the easiest way to interpret that value, because each percentile represents a cutoff at a different marker in the data set. I'll have some more examples of this in a little bit, but the median would be the first example of this because it is technically the 50th percent mark, or the 50th percentile. All right. Okay, so for the mean, we have to add all of the values together and then divide by the number of observations. So I'm just going to write here, so we'll have 417 plus 391 plus 419 plus 461 plus 472 plus 535 plus 622 plus 606 plus 508 plus 461 plus 390 plus 432 divided by 12. And that gives us 476.167. Okay. And then in this case, we can say something to the effect of, on average, there were 476.1667 airline passengers each month. Okay. All right. Okay, so the last value is the mode. So we're going to have a quantitative mode, and we're going to have a qualitative mode. So for the number of airline passengers, so for the quantitative variable, the mode is going to be the number that occurs the most. We can see from the ordered data set that the modal number is 461. So for the quantitative data, the mode is 461, which is just saying that most often, or it would be something to the effect of, we observed 461 airline passengers more often than any other number of airline passengers each month. Something like this. I'm a little short on room, but I'll try and fit that in after. But for the quantitative variable, the point is that the mode is the number that occurs the most. For the qualitative variable, so for the month of the year, what we are looking for here is the month that had the highest number of airline passengers. So we can see from the ordered data set that the highest number is 622. So that means that the qualitative mode would be July in this case. So you can see from the data set that 622 airline passengers traveled in July. So the month with the most traffic is July. So that becomes the modal month. So the interpretation of this is a little bit more straightforward, because in this case, we can just say July had the most airline passengers. So therefore it is the modal month, right? And so this would be month with most airline passengers, right? So again, for the qualitative variable, this is actually a pretty straightforward interpretation, because we're literally just describing the month of the year that had the most airline passengers, which in this case is July. But for the quantitative variable, which is the actual number of airline passengers that traveled, the mode in this case is going to be 461 again, because that's the number of airline passengers that occurred most often across the months of the year. Okay, so this would be number of passengers that occurred most often, something like this, right? Sorry, one sec. Okay, so Dakota, if the mean and median are the same, is the bell graph symmetric? Yeah, typically if they're close together, that would imply that the shape of the distribution is symmetric. It doesn't necessarily have to be a bell graph or a bell curve. So bell curves are typically associated with that unimodal shape, but we could have a distribution that isn't necessarily unimodal, but it is symmetric if those values are close together. Does that make sense? Okay, Jessica, for the mean, 476.2 would be incorrect. One more decimal place than the original data. So if the instructions say round to one decimal place beyond the original data, then your answer would be correct. But if there's no instruction about how to round, we typically just use 3 decimal places. So in this illustration, for example, we could just say 476.167. 3 is typically the standard if it isn't explicitly stated. Raleigh, how do we determine the qualitative mode? I understood it has nothing to do with the values. The qualitative mode would be, all right, so for the qualitative data, each of the months has an associated value. Okay, so if you think about like a bar chart, for example, the bar chart for this data set here would basically have the months of the year, January, February, March, April, May, would have the months of the year on the x-axis. And then on the y-axis, you would have some value, right? So the modal month is going to be the month that has the highest bar associated with it. So in this case, if we were to make a bar chart of the month of the year, the highest bar would belong to July, and that would make it the modal month. The other way that you could think about this is if you think back to the original qualitative data set that we worked with, which was the data set shown here. This data set has essentially listed out all of the different outcomes in the qualitative variable, right? So you have Renaissance appearing 10 times, for example, Mannerist appearing 6 times, et cetera, et cetera. If you go back to the data set that we're working on, you could actually do the exact same thing, except that it would just be a really big data set because you'd have January written out 417 times. You would have February written out 391 times. You would have March written out 419 times, etc. But in that case, you wouldn't have any raw data, but you would see that July occurs the most in that particular data set, which makes it the modal month because it's repeating most often. Does that make sense? Okay, sweet. Okay, any other questions about the exercise? Okay, so I mentioned before that the mean and the median, they are going to have a relationship with one another based off of the shape of the distribution. So there are 3 main shapes that we focus on in this course. They are the right skewed, the left skewed, and the symmetric shape. Though to be fair, those are the 3 shapes that, or those 3 terms would be the terms that we use most often when describing the distribution of a data set. Regardless of modality. So you still have skewness or symmetry, even if you have multiple peaks. I mentioned before that the median is most appropriate when the data is skewed, and the mean is most appropriate when the data is symmetric. So being able to describe the shape of the distribution of the data set is valuable because it can inform our choice of center. And I believe that this is, it's certainly one of the questions on assignment 1. I think it's in part B, and I think it's question 1 or question 2, but I might have the question number wrong. But that question essentially asks you to figure out which measure of center and measure of spread, we'll talk about that in a bit, is most appropriate. And so essentially what it's asking you to do is determine the shape of the variable and then use that to inform your choice. Okay, so in each of the different situations, so say we start off with the bell curve, right? So this is the middle. When we have a symmetric unimodal shape, both the mean and the median lie right at the center. So if we sort of just draw like a vertical line here, and then I'll use green. Okay, so this is going to be sitting effectively right on top. Yeah, so that was what I was afraid of. So these 2 lines are going to be right on top of each other. Okay, so I'll write this as a dashed line just so you can see it. Okay, so we have mean and we have median. Okay, so with symmetry, they line up at the same point, which is the middle. So both the mean and the median are going to fall at the center. So in this situation, we would recommend the mean, because the mean again is a function of all of the data. So it's a more informed measurement in that sense. So when we have this symmetric unimodal shape, we would suggest using the mean. In the other two situations, so when we have skewness in either direction, we're going to suggest the median. Now, what happens in this case? So here's my right skewed object. Here's my left skewed object. Okay, so what happens in this case is we're going to have the middle here and here. Okay, so in this situation, the median is still going to line up at the center. Oh no. Anyways. Okay. So in this situation, the median is still going to be at the middle, right? But the the mean gets pulled with the skewness. So in the case of right skewness, the mean kind of ends up over here, relatively speaking. So this isn't exact, but just the idea. And with left skewness, the mean ends up on the other side. So the mean, because it's a function of the actual data, so because it's calculated by adding all the values together, it gets pulled with the skewness. So when you have a right skewed object, the mean ends up being bigger than the median. So it's to the right of the median. And when you have a left skewed object, the mean ends up being less than the median. So it's to the left of the median. So in these two situations, we would recommend the median, right? Okay, and that's again because when you have skewness, the median is the only value that actually falls at the center. The mean is getting pulled with the asymmetry or with the skew tail. But when you have symmetry, they sit on top of each other. So you can go with either value, but we typically recommend the mean because it is actually it's based off of all the values in the data set. All right. Any questions about that relationship? All right. So we're going to move on to measures of spread next. The recommendations for the measures of spread based off of the type of data are going to be very similar. We're going to see that some measures of spread are a function of the mean. So therefore they would only be best when the data is symmetric. Whereas other measures of spread are not a function of the mean, but they are based off of percentiles like the median. So those would be best when the data is not symmetric. We call the median a resistant measure because it's not influenced by the observations. So basically, we say the median is resistant because the skewness does not pull it in either direction, whereas the mean would not be resistant because it gets pulled with skewness. The mode is, again, simply the value that occurs the most. So it's not truly a measure of center, though in the case of symmetry, the mode will be close to the middle of the data set. All three measurements have value. I mean, in the case of the qualitative variable, for example, the mode is the only value that actually applies. So that gives it a lot of meaning in that particular sense. And we can also see from the previous illustration that we can compare the mean and the median to get a sense of the shape of the distribution of the data set. Okay, as we move into measures of spread, we're going to introduce a new notation for calculating different statistical values. An example of this notation is shown in equation 1 on slide 37. This notation here is very common in statistical analysis because what it is used for is condensing formulae so that we don't have to write out the values in full. So, for example, we're going to start off by looking at the notation for the mean because we know how to calculate a mean based off of description. So we know that the mean is found by taking all of the values in the data set and adding them together and then dividing by the number of values. So the notation here is actually describing this process. So this first part here is a symbol that acts as one unit. Okay, so this symbol here, which is capital sigma, okay, so this part here is sigma. Sigma means add together the values between the indices. So what this is saying to us is add every value from the first observation. Okay, so this part here means first observation to the last observation. So this part here means the nth observation. Okay. So basically what this symbol is saying to us is add everything from the first value to the last value in the data set. So little n counts the number of objects in the data set. And then the xi term in here, this is a placeholder for a value in the data set. And this part here, this is number of values. Okay, so I'm going to show you what this means through example now, because typically just explanation like this doesn't really help with understanding of what this thing is actually telling you. So this is how it actually works. We have this data set that has 5 values in it. Okay, so we have 3.85, 4.42, 3.50, 2.07, 5.0. We want to compute the sample mean. All right, so our formula to compute the sample mean is going to be the sum from I equals 1 to little n of xi divided by little n. Okay, so this is how, here, actually, I'm going to move this over here so that it's a little bit more of a logical flow. Now, the first thing to remember is that the I equals 1 and the little n, that's attached to the sum. Those aren't separate values. It's all one quantity. Like it's basically a definition. So the sum, so sigma, I equals 1 to little n, is saying add up the values between I equals 1 and little n. Now, how does this actually apply to the values? Basically, what's happening here is we are assigning an x subscript I to each observation in the data set. So what we're saying is x1 is 3.85, x2 is equal to 4.42, x3 is equal to 3.50, x4 is equal to 2.07, x5 is equal to 5.00. Okay. So we're just letting each observation be called x subscript some number. So we have 5 observations in the data set. So x1 is the first number, x2 is the second number, x3 is the third number, etc. Right? Now, this also means that little n is going to be 5. So little n is the number of observations in the data set. So we have 5 values, so little n is 5. Okay, so that means that this formula here becomes the sum from I equals 1 to 5 of xi divided by 5. Okay, so that is x1 plus x2 plus x3 plus x4 plus x5 divided by 5. So that notation at the start, the I equals 1 to 5, the sum I equals 1 to 5, that's just saying add each x value from x1 to x5 together. So these two expressions here and this, that's the exact same thing. This shorthand notation is just telling us add up x1 to x2 to x3 to x4 to x5. Okay, and now this thing is going to become exactly what we're used to. Sorry, Elizabeth, I just saw that. So it's sigma. M. Okay, so now this expression is going to turn into exactly what we're used to. So now we're just going to sub in. So 3.85 plus 4.42 plus 3.50 plus 2.07 plus 5.00 divided by 5. And that gives us 3.768. Now, again, it's important to remember that this isn't changing the definition of the mean or changing the definition of the average. That value is always all of the numbers added together divided by the number of values. Always. Like that is the true verbal definition of the mean. This notation shown here. So this notation here, the summary notation. This is something that we introduce so that we can write the formula out in a more condensed way. And as you're going to see momentarily, with values like the standard deviation, summary notation is very important because that formula is more complex than just the average. I like to use the average to introduce the notation because students tend to struggle with what it means. But we're going to look at more examples of this momentarily in slightly more complicated situations. But hopefully by starting from this illustration, that next extension will be a little bit easier to digest. Exactly. So whenever you see sigma, sorry, I'm going to go backwards here. So shall be, the notation just means add up all the values. Yes, that is correct. So this notation just means add everything together. Annalise, do significant digits need to be considered in the answer here? Yeah, so typically what we would do in these situations is we would hold as many significant digits as we can through the calculation, and then we would round at the end. Now, I recognize at the end, I now have 3 decimal places. If the question states like round to 1 decimal place or keep it at the number that are originally given, then you can round to 1 or to 2. But in general, again, we usually round to 3 for our final answer. We'll talk a little bit more about that too in the next step, because with more complicated calculation, you want to hold more decimal places or more significant digits in the intermediate steps of the calculation, and then round to a smaller number in the end. Does that answer your questions? Okay, sweet. All right, so we talked about measures of center. So we have the mean, the median, and the mode. For symmetric objects, the mean is the best measure of the recommended measure of center. For skewed objects, the median is the recommended measure of center. We're going to talk now about measures of spread. Measures of spread are used to give us a sense of how far the points are deviating from the middle. So when you think about the shape of a distribution of the data set, let's say we have that unimodal symmetric shape. We know that the midpoint is going to be the mean or the median. But we know that there's a lot of information on each side of that value. So it's not like the data set just sits fixed at that one point and nothing changes. That midpoint describes the midpoint of the shape that we're describing. So what we want to do now is try and describe all of the area under the curve that sits on either side of that midpoint. So that's what our measures of spread are for. They are a value that is allowing us to understand how the data flows from the midpoint of the distribution. There are many different measures of spread. For example, there's the range, which is a very easy value to calculate. And then we have things like the sample standard deviation and the sample variance, which are more complicated. And then values like the interquartile range or percentiles in general, which are not difficult to calculate, but there are many of them and they all require sort of separate interpretation based off of their location. So we're going to look at examples of all of these points. Once we describe the interquartile range, we're going to turn back to the box plot, which is a visualization I mentioned earlier to describe the distribution of the data set. Okay, so the first measure of spread is the range. The range is simply the difference between the biggest value and the smallest value. So it's very easy to calculate. It's just maximum value minus minimum value. So it's one number and it's telling us the total distance between the biggest point and the smallest point. Okay. The sample standard deviation is a value that we are going to use very often throughout the course. The sample standard deviation would be a measure of spread that we recommend when the data is symmetric. Okay. Now, the reason that we use this value when the data is symmetric is because you can see that it is a function of the mean. Okay. So we know that the mean is only at the center when the data is symmetric. So therefore, the standard deviation which utilizes the mean, is really only appropriate when the data is symmetric. Okay. All right, now we're going to look at some examples of how to actually calculate this value, because as you can see, this value also uses the summary notation that we had just discussed. So this is a slightly more complex formula, but it's based off of the same notation that we have just learned about. So even in this situation here, the sigma I equals 1 to n still means add up all the values. But now what it's saying to us is add up the xi minus x bar all squared from I equals 1 to n. Yeah, contains sample mean, sorry. Yeah, sorry, bad rating. Okay, so this value, we're going to learn how to calculate it, and we're going to work through an example like the one that we saw for the mean, just so that we can get comfortable with the notation. Right? And then we're going to look at a different way to calculate it. So there's actually two ways to calculate this value. On the assignment, you have the choice of doing it either way. In general, the second way is the way that we recommend because it's a bit faster. Right? Okay, so here's an illustration of how the calculation of this value would unfold. So we're using the same data set that we used to demonstrate the calculation of the sample mean, right? So we have 5 observations. We have let each observation have an X subscript notation. So X1 is 3.85, X2 is 4.42, X3 is 3.50, X4 is 2.07, X5 is 5.00. All right, we know from our previous work that X bar is 3.768. So this is what we calculated 2 or 3 slides back. Okay, in the notation for the standard deviation, what we are told, oh, I have it right here, is that we want to add, so add up xi minus x bar squared. So the first thing that we do is we compute the xi minus x bar, right? So that's what is done here. Okay, so this can be step 1. So we take xi and we subtract the mean. So we have 3.85 minus 3.768 is 0.082. Then we have 4.42 minus 3.768 is 0.652. And then we have 3.50 minus 3.768 is negative 0.268. And then we just continue with that process. Okay, so we have 5 differences. Then what we do is we square each of those values. So 0.082 squared is 0.00672. 0.652 squared is 0.45210. Negative 0.268 squared is 0.07182, etc. All right, now, because we want to add up each of the squared differences, we can take the values in the last column and we can add them together. So this 4.90466, this is the sum of these 5 values above it. Okay, so step 3 is just adding those differences together. Okay, now from this point, we can just plug into our formula directly. So you can see here on the last line, I have the square root of 4.90466. So I'm taking the sum in step 3 and I'm plugging it into the formula. So now I have the square root of 4.90466 over 5 minus 1. And that gives me the square root of 1.22617, which is 1.107. All right. Okay. So now what I want to do is I want to go through a different exercise of this where we start from scratch so we can see how this unfolds. And then if there's questions about it, the exercise might clear them up, but if not, then obviously we'll pause for questions after that. So we're going to repeat this exact process, but we're just going to do it together starting from scratch. I added. Okay, so the question is, so you added all the values and squared them, and that's 4.90466. No, so I squared all of the values and then added them. So I just did slightly different order. So I squared the values first, and then I added them together. So this would be 0.0672 plus Does that make sense? So square and then add. Yeah. Okay. Oh. Oh, okay. Sorry. So we're going to do an exercise. So that whole spiel I just gave about doing an exercise is going to happen. I'm just going to show you the other way of doing it, and then we're going to do them together. Okay. So this approach here in exercise 1. So this formula is called the defining formula, right? So this is our defining formula. So this is one way of computing S, which is the sample standard deviation. The other way that we can compute S is using the computing formula, which is shown here, okay? Now, this formula also uses the summation notation, but it's technically a faster way to get to the answer because we don't have to do the because we don't have to do the differencing. But equation 3, the defining formula, and equation 4, the computing formula, are two ways of doing the exact same thing. So on the assignment in question number 2, you have to compute little s for the temperatures that are given. I believe it's temperatures. You can use either formula. So you can use the defining formula, the one that we just looked at, or you can use the computing formula, which is the one shown here. They will give you the exact same answer. So actually, the other thing you can do is do both, and then you can check your solution because they should match up. So it's sort of a built-in way of checking your value. So Elizabeth, the first formula, this one here, this is the defining formula. Okay, so let's look at an example of how this is computed, and then we'll go through that exercise that I was talking about before. All right, so the computation of the computing formula is meant to be a little faster than the defining formula. The idea here is pretty much exactly the same as it was before. So we're going to have x1, x2, x3, x4, x5. Okay, so this is going to be 3.85. This is going to be 4.42. This is going to be 3.50. This is going to be 2.07. And this is going to be 5.00. Okay, so the sum from I equals 1 to little n of xi, this is going to be the same definition we saw for the mean. So this is just going to say add up all of the values in the data set. It's worrying me that my writing is getting worse and worse. Okay, so that's where the 18.84 comes from. So that's just the sum of the numbers together. Now, the second part in the computing formula is the sum of each xi value squared. So what this means is 3.85 squared plus 4.42 squared plus 3.50 squared plus 2.07 squared plus 5.00 squared equals 18. Oh, sorry. Equals 75.8938. So this is effectively why the computing formula is considered to be a faster formula for getting little s, because you just have to add the values together, and then you just have to add each value squared together. And then once you have these two numbers, we're just subbing into equation 4. Okay. So on slide 44, you can see how this process unfolds. So we have the square root of the sum from I equals 1 to n of xi squared. So that's the 75.8938 minus the sum of the xi all squared. So that's the 18.84 squared divided by 5 all over 5 minus 1. And then you work that out and you end up at the exact same quantity that we had on slide 42. Okay, and you'll see that those two numbers match up. Any questions? Yes, that is correct. So Shelby, so the question is, we can use either formula when it doesn't specify, and the answer is yes, you can use either formula. In general, I recommend the computing formula unless the question gives you information that would make the defining formula faster, like it gives you the squared differences or something like this. But the computing formula is generally a bit easier and a bit quicker to get to the solution. So like on the assignment, you can use either formula, for example. Okay, so let's work through an example of computing both, or of using both the defining formula and the computing formula. All right, give myself lots of room. Okay, so we have the following data set gives the girth of black cherry trees in inches. All right, so as a reminder here, okay, so this is going to be the variable. Okay, so we are measuring the girth of black cherry trees. Okay, we have 6 observations. We want to calculate the standard deviation and verify the result. So effectively what this means when it says verify is compute in 2 different ways. So we want to check our work. So we're going to use the defining formula, and then we're going to use the computing formula. And then we're going to check to see if those 2 answers match up, which we know they should. All right, so we'll start off with the defining formula. So we have S is equal to Okay, so to compute this value, we're going to construct a table. All right, so here we're going to have xi. So this is going to be 8.3, 10.5, 11.1, 12.9, 13.8, 14.5. Okay, in the second column, we're going to go xi minus x bar. All right, so the first problem, we need to figure out what x bar is. Okay, so we know x bar is going to be the sum from I equals 1 to n of xi divided by little n. And actually, I'm just going to make a note here. Find or calculate this. So step 1, calculate this. Okay, so we know that this basically just means we want to add the values together. And divide by the number of values. So that gives us 11.85. Right? Okay, so now what we're going to do, I'm just going to move this over so we have a little more room here. So now what we're going to do is we're going to take each value, subtract the mean. So as an example, we're going to have 8.3 minus 11.85 is equal to negative 3.55. And then we're going to have 10.5 minus 11.85 is equal to negative 1.35. And then we're going to have 11.1 minus 11.85 is equal to negative 0.75. Then we're going to have 12.9 minus 11.85 is equal to 1.05. Then we're going to have 13.8 minus 11.85 is equal to 1.95. And then we're going to have 14.5 minus 11.85 is equal to 2.65. Okay, and then we're going to square each of those numbers. So now we're going to have negative 3.55 squared is equal to 12.6025. Good enough. Okay. And then we'll have negative 1.35 squared is equal to 1.8225. And then we'll have negative 0.75 squared is equal to 0.5625. 1.05 squared is equal to 1.1025. 1.95 squared is equal to 3.8025. And then we have 7.0225 squared is equal to, oh no, sorry. 2.65 squared is equal to 7.0225. All right. Okay, so our defining formula, which was written above, says take the square root of the sum from I equals 1 to little n of xi minus x bar squared divided by n minus 1. Okay. So what we have here is 12.6025 plus 1.8225 plus 0.5625 plus 1.1025 plus 3.8025 plus 7 point, no. Plus 7.0225. Divided by 6 minus 1. Okay, so this is going to give us the square root of 26.915 divided by 5, which is the square root of 5.383, which is equal to 2.320. Right. So that's the defining formula. And you can see from the illustration, right, like this is a fairly tedious calculation, especially because of the construction of the table, going through the process of putting the numbers together, making sure that you have things in the right place. It just takes a little longer than the computing formula does. All right. So for the computing formula, we have S is equal to the square root of the sum from so we have the sum from I equals 1 to n of xi squared minus the sum I equals 1 to n xi all squared over n divided by n minus 1. So in this situation, we need to work out the sum of the xi squared and the sum of the xi so that we can square that number. All right. So we have the sum from I equals 1 to n of xi. So we actually worked this out above, or we wrote this out already. So this is going to be the 8.3 plus the 10.5 plus the 11.1 plus 12.9 plus 13.8 plus 14.5. And that gives us 71.1. And then we have the sum from I equals 1 to n of each xi squared. So this is going to be 8.3 squared plus 10.5 squared plus 11.1 squared plus 12.9 squared plus 13.8 squared plus 14.5 squared, which is 869.45. Right? So you can already see like the process for getting to the solution via the computing formula is much quicker. Those two calculations took a fraction of the time that it took us to construct that table of differences used for the defining formula. So now all we have left to do is plug in, right? So we're going to have 869.45 minus 71.1 squared over 6 divided by 6 minus 1. So this is the square root 869.45 minus 842.535 divided by 5. And then this is going to give us the square root of 26.915. So you can see now that we have converged to the same answer that we had before. And we end up with the same solution. Okay. Any questions? What is below the sigma symbol? I equals 1. Okay, so this is the same. It's the same thing that's been written on each of the slides. So it's always sigma I equals 1 to little n. So you can write it beside it or below it. I sort of migrated to writing it below it. It just gives me a little more room, but it's just I equals 1 to n. So it's always the same thing. Could you explain how you would interpret the standard deviation for this example? Yep. So for the standard deviation, we usually have, let me see if I can find a good expression for it. Essentially, what the standard deviation measures is the expected difference between the mean and the remaining points in the data set. So an interpretation of this, 2.320. Okay. So, all right. Here's one way that you could do it. So first off, I'll come back to it really quickly here, Mackenzie, but so what the standard deviation is doing is it's telling us how far on average the observations are from the mean. Okay, so in general, when we have a small standard deviation, that it means that values are very close to the mean. And when we have a larger standard deviation, that means that the values are quite far from the mean. So in the context of this problem, we could say something like, on average, the girths of, I think they're black cherry trees, wait, yeah. The girths of black cherry trees fall 2.32 inches on, or fall 2.32 inches from the mean, essentially. So we're just saying what the value is, again, is basically just a measurement of how far the observations are from that mean. So in this case, we would basically just say that the standard deviation is telling us that from the mean, the girths range 2.32 inches in either direction. So we can be 2.32 inches smaller than the mean, up to 2.32 inches bigger than the mean on average. Does that make sense? Sweet. Okay. 916. Okay, so that's that brings us to the end of the first set of values of spread. So we have to finish off with one other main set of values of spread, which are the percentiles. So on Thursday, we're going to talk about percentiles because obviously I'm not going to have enough time to do it today. Just before we finish though, I want to bring your attention to the sample variance. It's not a measurement that we're going to see too often, but you can see that the sample variance is essentially just the square of the sample standard deviation. Right? So equation 5 is giving us the exact same formula as equation 3, except we're not square rooting. So the standard deviation is the square root of the variance, and the variance is the square of the standard deviation. In general, they give us the same idea, but the standard deviation is a preferred measure because it actually is on the same scale as the variable. Whereas the variance would be on the squared scale, so it's a bit more difficult to interpret. All right. Okay, so Raleigh, it is a more precise range. It's a representation of how far the values are spreading out from the mean. So under the assumption that the data is symmetric, it represents how far away the values are ranging from the mean. So it's not a range. It's not a range. The range is the difference between the smallest and the largest value. It's a representation of distance from the mean, I guess you could say. Kareem, so on Thursday, we're going to finish lecture set 2, and all of the material that you need for assignment 1 will be given in lecture set 2. So nothing next Tuesday would be included on assignment 1. Kavir, that's a typo. So this is our 4th lecture of the semester. So we've done lectures 1, 2, 3, 4. Okay, so on Thursday, we'll finish lecture set 2. Once we finish lecture set 2, we'll pause and take some questions for the assignment, and then we'll move into lecture set 3. Okay, so I'll see you guys on Thursday morning. If anyone has any questions, I'll hang around after class. And otherwise, have a good couple of days, and I'll talk to you then.